The universe is far from silent. Beneath the vast expanse of stars and galaxies lies a hidden symphony, ripples in the very fabric of spacetime, echoing the most dramatic events in the cosmos. These are gravitational waves, cosmic messengers that carry stories of colliding black holes, exploding stars, and even the birth of the universe itself. Imagine, for a moment, being able to hear these waves, to listen in on the universe's most powerful events as they unfold billions of light years away. What secrets do these ripples hold, and how do they reshape our understanding of the cosmos? In this video, we'll dive into the science behind gravitational waves, uncover their history, and explore how they're weaving a cosmic tapestry that connects us to the farthest reaches of space and time. Get ready for an awe-inspiring journey into the hidden symphony of the universe, a story written not in light, but in the very warp and weave of spacetime itself. In the early 20th century, Albert Einstein revolutionized our understanding of the universe with his theory of general relativity. Published in 1915, it proposed that massive objects like stars and planets don't just sit in space. They warp the very fabric of spacetime around them. Imagine placing a bowling ball on a trampoline. The dent it creates is like how a star curves spacetime, but Einstein didn't stop there. He predicted that when massive objects accelerate or collide, they should send ripples through this cosmic fabric, ripples we now call gravitational waves. For decades, these waves remained theoretical, a ghostly whisper in the equations of physics. But then, in 2015, something extraordinary happened. Scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first direct evidence of gravitational waves, the source. Two black holes, each dozens of times more massive than our Sun, spiraling into each other over 1 billion light-years away. The collision sent a tremor through spacetime, a ripple so faint it took decades of technological innovation just to measure it. Think of it like dropping a stone into a still pond. The ripples spread outward, growing fainter as they travel. Gravitational waves work the same way, but instead of water, they travel through the fabric of the universe itself. And just like ripples on a pond, they carry information about the objects that created them, information that would otherwise be lost in the vastness of space. The detection in 2015 wasn't just a scientific milestone. It was a confirmation of Einstein's genius, proving a prediction made a century earlier. But capturing these ripples wasn't easy. The signals are incredibly faint, requiring instruments so precise they can detect changes smaller than a fraction of an atomic nucleus. It's like trying to hear a whisper in a roaring stadium, a feat that pushes the boundaries of human ingenuity. This discovery opened a new window into the cosmos, one that doesn't rely on light or electromagnetic waves, but instead listens to the vibrations of spacetime itself. And as we'll see next, the precision required to detect these cosmic whispers is nothing short of breathtaking. To truly grasp the wonder of gravitational waves, let's start with the fabric of the universe itself, spacetime. Picture spacetime not as an empty void, but as a dynamic, stretchable sheet like the surface of a trampoline. When massive objects like stars or black holes move or collide, they create ripples in this fabric, much like tossing a pebble into a still pond. These ripples are gravitational waves, distortions that travel outward at the speed of light, carrying energy and information from their source. Now, imagine two black holes locked in a cosmic dance, spiraling closer and closer until they merge. As these colossal objects accelerate, they send shock waves through spacetime itself, creating waves that can stretch and compress everything in their path. The frequency of these waves depends on the size and speed of the objects involved. For example, a pair of stellar mass black holes might produce waves with frequencies in the hundreds of hertz, while supermassive black holes generate waves so low they're almost imperceptible. To make this even more relatable, think of gravitational waves as cosmic sound waves. Just as sound travels through air, gravitational waves travel through spacetime, vibrating the very fabric of the universe. But unlike sound, which we hear with our ears, these waves are detected by incredibly sensitive instruments that measure the tiniest shifts in distance, shifts smaller than the width of an atom. What makes gravitational waves truly extraordinary is the information they carry. Each wave encodes details about its source, whether it's the collision of black holes, the explosion of a supernova, or the birth of a neutron star. By analyzing these waves, scientists can uncover secrets about the most violent and energetic events in the cosmos, offering a new way to listen to the universe. And yet, detecting these subtle whispers from the cosmos is no small feat. It requires technology so precise it borders on the miraculous, capable of measuring distortions 1 billion times smaller than an atom. This brings us to the next chapter of our journey, the groundbreaking instruments and human ingenuity that make this incredible science possible. Imagine trying to hear a whisper in the middle of a roaring concert. That's the kind of challenge scientists faced when they set out to detect gravitational waves, ripples in space. I'm so faint that they're nearly drowned out by the noise of our planet. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory, a marvel of engineering designed to listen to the faintest murmurs of the universe. This isn't just any instrument, it's the most sensitive detector ever built, capable of measuring distortions in spacetime thousands of times smaller than the width of a single proton. LIGO design is as elegant as it is ambitious. Picture two enormous arms, each stretching several kilometers long, arranged in a perfect L shape. At the heart of this setup are laser beams that race down these arms, bouncing off mirrors at the ends. When a gravitational wave passes through, it warps spacetime ever so slightly, causing one arm to stretch while the other compresses. This tiny change alters the laser beam's paths, creating an interference pattern that scientists can measure. It's like using light to weigh the fabric of the universe itself, but building LIGO was no small feat. Its development spanned decades, involving thousands of scientists and engineers from around the globe. This was a project that demanded not just technical brilliance, but also an extraordinary level of collaboration. Think about it. Isolating a detector from Earth's constant vibrations, temperature fluctuations, and even the faint hum of distant traffic required innovations that pushed the boundaries of what was possible. Suspended mirrors, vacuum tubes, and seismic isolation systems were just some of the tools used to shield LIGO from the noise of everyday life. The challenges didn't stop there. Even after LIGO was built, fine-tuning it to detect gravitational waves required years of painstaking calibration. Every click, every tremor, every whisper of interference had to be accounted for. It was a monumental effort, a testament to human ingenuity and perseverance, and when LIGO finally succeeded in detecting its first gravitational wave in 2015, it wasn't just a triumph for science, it was a moment that changed our understanding of the cosmos forever. This incredible instrument has given us a new way to observe the universe, one that doesn't rely on light or electromagnetic waves, but on the very fabric of spacetime itself. It's a reminder that sometimes, to hear the universe's secrets, we need to build tools that can listen in ways we never thought possible. And as we'll see, the story of what LIGO has uncovered is just as extraordinary as the instrument itself. In September of 2015, the world of science experienced a moment that would forever change our understanding of the universe. For the first time in history, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected ripples in spacetime, gravitational waves emanating from the collision of two black holes over 1 billion light-years away. The signal, lasting just a fraction of a second, was so faint that it took months of painstaking analysis to confirm its authenticity. Scientists were both exhilarated and incredulous. After decades of searching, they had finally captured the elusive whispers of spacetime itself. This discovery wasn't just a scientific achievement, it was a cosmic milestone. For centuries, we've relied on light to explore the universe, but gravitational waves offered something entirely new, a way to listen to the cosmos. Imagine being deaf to the world and suddenly hearing the roar of an ocean or the rustle of leaves. That's what this moment felt like for humanity. It was as if the universe had handed us a new set of ears, allowing us to perceive events that were once hidden in silence. The significance of this breakthrough cannot be overstated. It confirmed a key prediction of Einstein's theory of general relativity, proving that spacetime is not a static backdrop but a dynamic, rippling fabric. This monumental achievement earned the LIGO team the Nobel Prize in Physics in 2017, cementing their work as one of the most important scientific discoveries of our time. And yet, this was only the beginning. With gravitational waves, we've unlocked the ability to observe the universe in an entirely new way, revealing not just black holes, but neutron stars, supernova, and perhaps even echoes from the Big Bang itself. Picture two black holes, each with a mass millions of times greater than our Sun, locked in an intricate dance. As they spiral closer and closer, their immense gravitational pull warps the fabric of spacetime around them. This isn't just a cosmic spectacle, it's a drumroll, building toward a moment that sends shockwaves across the universe. When these black holes finally collide, they unleash a burst of energy so powerful that it distorts spacetime itself, sending out ripples known as gravitational waves. These waves travel at the speed of light, carrying with them the story of the collision, the masses of the black holes, and even the way they were spinning. Simulations of these events are breathtaking. They show the black holes spiraling inward, their orbits tightening as they lose energy to gravitational waves. The closer they get, the faster they move until, in a final, explosive moment, they merge into a single, more massive black hole. The new black hole doesn't settle quietly, though. It vibrates or rings down like a bell struck by a hammer, emitting gravitational waves that gradually fade away. These ripples are like cosmic fingerprints, revealing details about the black hole's masses, spins, and even their origins. But what's truly remarkable is what these collisions teach us. By studying the gravitational waves from black hole mergers, scientists can piece together how these colossal objects form and grow. Some black holes might have started as massive stars that collapsed under their own gravity, while others could be the result of earlier mergers. The spins of the black holes can also tell us about their history, whether they were born spinning rapidly or gained momentum as they danced toward each other. And while black hole collisions are some of the most dramatic sources of gravitational waves, they're not the only ones. Just as fascinating are the events involving neutron stars, tiny, incredibly dense remnants of exploded stars. When neutron stars collide, they create a different kind of gravitational wave signature, one that's accompanied by bursts of light and even the creation of heavy elements like gold and platinum. But that's a story for another moment. For now, let's marvel at the cosmic drumroll of black hole mergers, a phenomenon that reminds us just how dynamic and interconnected the universe truly is. Picture this: two incredibly dense neutron stars, each packing the mass of our Sun into a city-sized sphere, spiraling toward each other in a cosmic dance. As they draw closer, their immense gravitational pull warps spacetime, sending ripples, gravitational waves across the universe. But that's just the beginning. When these stars finally collide, it's like the ultimate cosmic fireworks show. The merger doesn't just send out gravitational waves, it also unleashes a burst of light across the entire electromagnetic spectrum, from gamma rays to visible light. This dazzling display isn't just beautiful, it's a scientific goldmine. In 2017, scientists witnessed one of these rare events for the very first time. LIGO, the gravitational wave detector, picked up the ripples in spacetime, and within moments, telescopes around the world turned their gaze to the same patch of sky. What they saw was extraordinary. The collision produced a kilonova, a brilliant explosion that confirmed something astronomers had long suspected. Neutron star mergers are cosmic forges, creating heavy elements like gold, platinum, and uranium. That single event produced more gold than the mass of our entire planet. It's humbling to think that the ring on your finger or the circuitry in your phone might owe its existence to an ancient cosmic collision billions of years ago. This groundbreaking discovery marked the dawn of multi-messenger astronomy, a revolutionary approach that combines gravitational waves with traditional light-based observations. By studying the same event through different lenses, scientists can piece together a far richer picture of the universe. Gravitational waves tell us about the collision itself, the masses, speeds, and distances involved, while light reveals the aftermath, the chemical makeup of the debris, the energy released, and even the environment around the merging stars. Together, they offer a more complete story than either could tell alone. The implications of these discoveries stretch far beyond the stars. By understanding how elements form and spread through the cosmos, we gain insight into the very building blocks of life. It's a reminder that the universe isn't just a vast, empty expanse, it's a dynamic, interconnected system, where even the most distant events can shape the world we live in. And as we continue to refine our tools and techniques, who knows what other cosmic secrets we'll uncover? The universe is full of surprises, and each discovery brings us one step closer to understanding the grand tapestry of existence. The universe, in its earliest moments, was a symphony of unimaginable energy and motion. But how do we tune into the echoes of that ancient cosmic song? Gravitational waves, those ripples in spacetime, might just hold the key. Imagine these waves as the universe's oldest recordings, carrying whispers of a time when everything we know was compressed into a single, infinitely dense point. These aren't just any gravitational waves, they're primordial gravitational waves, forged in the fiery aftermath of the Big Bang itself. During the universe's first fraction of a second, it underwent an explosive growth spurt known as cosmic inflation. This rapid expansion stretched spacetime itself, leaving behind faint imprints in the form of gravitational waves. Think of it like the universe's first drumbeat, reverberating through the fabric of reality. These waves are unique because they're not tied to cataclysmic events like black hole collisions or neutron star mergers. They're relics of the universe's birth, carrying clues about its earliest moments. Detecting these primordial waves could be a game changer for cosmology. They'd allow us to test theories like cosmic inflation, which suggests the universe expanded faster than the speed of light in its first moments. If we could observe these waves, we might finally answer questions like, what triggered the Big Bang? What was the universe like before it began to cool and form matter? The answers are hidden in these ancient ripples, waiting to be decoded, but here's the catch: these signals are incredibly faint. They've traveled across nearly 14 billion years of cosmic history, and by the time they reach us, they're barely a whisper. Detecting them requires technology so precise, it can measure distortions in spacetime smaller than the width of an atom. It's like trying to hear a single note in a cacophony of cosmic noise. And yet, the pursuit is worth it, because these waves could unlock secrets about the universe that no other tool can reveal. As we push the boundaries of science to detect these ancient signals, we're reminded just how much of the universe remains a mystery. The challenges are immense, but so are the rewards. What if these primordial waves hold the key to understanding not just our origins, but the very nature of reality itself? The search for primordial gravitational waves is like trying to hear the faintest whisper in a crowded room. These ripples in spacetime, created in the earliest moments of the universe, carry secrets about how everything began. But detecting them is no small feat. Scientists are turning to the cosmic microwave background, or CMB, for clues. This ancient light, dating back to just 380,000 years after the Big Bang, acts like a cosmic snapshot, a frozen moment in time that might hold the fingerprints of those primordial waves. When the universe was a seething, chaotic soup of energy, gravitational waves from its birth could have left subtle imprints on the CMB. Think of it as a cosmic photobomb, where the ripples in spacetime subtly warp the light we see today. Detecting these patterns requires cutting-edge technology and a meticulous eye. Experiments like the BICEP and Keck Array telescopes in Antarctica scan the skies, searching for a specific signature called B-mode polarization. This swirling pattern in the CMB could be the smoking gun of primordial gravitational waves, but here's the catch: the universe is full of noise, dust in our galaxy, emissions from distant stars, and even the afterglow of the Big Bang itself can muddle the signal. Sorting through this cosmic static demands not just precision but innovation. Future space-based observatories, like the proposed Light Bird mission, aim to escape Earth's interference entirely. By placing detectors in the quiet expanse of space, we could finally isolate those elusive whispers from the early universe. These advancements aren't just about technology, they are about unlocking the story of our cosmic origins. If we can detect primordial gravitational waves, we'll gain a window into the universe's first moments, confirming theories like inflation that describe how the cosmos expanded faster than light in its infancy. It's a quest that bridges the realms of cosmology and engineering, pushing the boundaries of what we know and how we explore. And with space-based observatories leading the charge, the next chapter in gravitational wave astronomy promises to be nothing short of revolutionary. Imagine a symphony so vast that its notes ripple across the cosmos, carrying secrets of the universe's most cataclysmic events. Now, picture a trio of spacecraft floating in the quiet expanse of space, poised to listen to this hidden music. This is the Laser Interferometer Space Antenna, or LISA, a groundbreaking mission designed to detect gravitational waves from the depths of space. Unlike ground-based observatories, LISA will operate far from Earth, where it can pick up the faintest whispers of these cosmic ripples. At the heart of LISA design are 3 spacecraft, arranged in a precise triangular formation. Each side of this triangle spans millions of kilometers, making it the largest scientific instrument ever built. These spacecraft will use laser beams to measure the tiniest distortions in spacetime caused by passing gravitational waves. Think of it like an enormous cosmic microphone, tuned to frequencies far below what we can detect on Earth. What makes LISA so extraordinary is its ability to hear the low-frequency hum of the universe. These are the waves produced by events like the merging of supermassive black holes, collisions that shake the very fabric of spacetime. With LISA, we'll be able to map these colossal encounters, revealing how galaxies evolve and grow over billions of years. But that's just the beginning. LISA could also help us uncover the large-scale structure of the universe, tracing the invisible web of dark matter that binds everything together. And then there's Einstein's theory of general relativity. LISA will put it to the test in ways we've never imagined, probing the limits of our understanding of gravity itself. Could there be deviations from Einstein's predictions? Or perhaps entirely new physics waiting to be discovered? What's truly inspiring about LISA is the collaboration behind it. Scientists and engineers from around the world are coming together to make this mission a reality, proving that the quest to understand the cosmos is a shared human endeavor. This spirit of cooperation is what drives gravitational wave research forward, reminding us that the universe's secrets are best unlocked when we work together. The discovery of gravitational waves wasn't just a triumph for a single team or country. It was a monumental achievement made possible by a truly global effort. Scientists from dozens of nations, representing hundreds of institutions, have come together to build and maintain the intricate network of detectors that listen to the whispers of the cosmos. At the heart of this collaboration are three key observatories: LIGO in the United States, Virgo in Italy, and CAGRA in Japan. Each of these facilities plays a critical role in the hunt for gravitational waves, but it's their combined power that makes the difference. When a gravitational wave passes through Earth, it doesn't just hit one detector. It ripples across the globe. By having observatories spread across different continents, scientists can triangulate the source of these waves with incredible precision. Think of it like trying to locate a sound in a dark room. If you only have one ear, it's hard to tell where the noise is coming from, but with multiple ears, you can pinpoint the exact direction. That's exactly what LIGO, Virgo, and CAGRA do for the universe. Together, they create a kind of cosmic GPS, allowing researchers to trace the origins of these elusive signals to distant galaxies, colliding black holes, or even the remnants of ancient stars. This global network doesn't just improve accuracy, it also expands the range of events we can detect. A single observatory might miss a faint signal, but when multiple detectors work in unison, they can catch waves that would otherwise slip through the cracks. It's a bit like having a team of astronomers with different telescopes, each one contributing a unique piece of the puzzle. The result, a richer, more detailed picture of the universe's most violent and energetic events. But as powerful as this collaboration is, it's not without its challenges. Gravitational wave data is incredibly complex, filled with subtle distortions and background noise that can make interpretation a daunting task. Scientists must sift through mountains of information, separating the faint signals from the cosmic static, and even when they find something promising, deciphering what it means requires a deep understanding of physics, mathematics, and the behavior of spacetime itself. It's a process that demands patience, precision, and a global effort to ensure that every discovery is as accurate as possible. Gravitational waves are like cosmic fingerprints, carrying unique information about the events that created them. But how do scientists decode these faint ripples in spacetime? It all starts with the data collected by detectors like LIGO and Virgo. These instruments capture the waves, but the raw signals are often buried under a sea of noise. Everything from seismic vibrations to passing trucks can interfere. To isolate the true gravitational wave signals, researchers rely on supercomputers and advanced algorithms. These tools sift through the noise, searching for patterns that match the theoretical models of cosmic events like black hole mergers or neutron star collisions. Once a potential signal is identified, the real detective work begins. The shape, frequency, and amplitude of the wave provide crucial clues about its source. For example, the frequency of the wave can reveal the masses of the objects involved. A higher frequency often indicates smaller objects, like neutron stars, while lower frequencies point to more massive entities, such as black holes. The amplitude, or strength, of the wave helps scientists estimate how far away the event occurred. A stronger signal typically means the source is closer, while a weaker one suggests it's more distant. But it doesn't stop there. The spin of the objects can also be inferred from the waveform. If the merging objects were spinning rapidly, their gravitational waves carry a distinct signature, like a cosmic fingerprint with a unique swirl. By comparing the observed signals to detailed simulations, scientists can piece together the story of these cataclysmic events, what the objects were, how they behaved, and even how they met their dramatic end. This process isn't just about decoding the past, it's also shaping the future of astronomy. Gravitational waves open a new window into the universe, allowing us to observe phenomena that were once invisible. From black holes colliding in the depths of space to neutron stars spiraling together, these signals are rewriting our understanding of the cosmos. And as our tools and techniques improve, who knows what other mysteries will uncover? The universe is full of secrets, and gravitational waves are helping us listen to its hidden symphony. The universe speaks to us in many languages, and gravitational waves are just one of its voices. But what happens when we listen to all of them at once? This is the heart of multi-messenger astronomy, a groundbreaking approach that combines gravitational waves with light, neutrinos, and even cosmic rays to paint a fuller picture of the cosmos. Imagine trying to understand a symphony by hearing only one instrument. Multi-messenger astronomy allows us to hear the entire orchestra, revealing the universe's most dramatic events in stunning detail. Take gamma-ray bursts, for example. These are some of the most energetic explosions in the universe, often signaling the birth of black holes or the collision of neutron stars. Before gravitational wave detectors, we could only observe these events through the light they emitted, but now, with tools like LIGO and Virgo, we can also hear the ripples in spacetime they create. When combined with data from telescopes and neutrino observatories, these signals give us a multidimensional view of the event, helping us piece together its origin, energy, and aftermath. Supernova, too, are part of this cosmic symphony. These colossal star explosions scatter elements like iron and gold across the universe, seeding future stars and planets. By pairing gravitational wave observations with electromagnetic signals, we can study the final moments of a star's life in unprecedented detail. It's like watching a movie with both the sound and the picture. Each enhances the other, creating a richer experience. But the real excitement lies in what we haven't yet discovered. Multi-messenger astronomy opens the door to entirely new phenomena. What happens when black holes collide with neutron stars? Could we detect the elusive quantum ripples from the Big Bang itself? Each new observation has the potential to rewrite our understanding of the universe, revealing secrets we didn't even know to look for. And as we gather more data, we're not just answering scientific questions, we're also asking deeper ones. What does it mean to see the universe in so many ways? How does this new perspective change our place in the cosmos? These discoveries remind us that the universe is far more complex and interconnected than we ever imagined, and that every new insight brings us closer to understanding its grand design. Gravitational waves have done more than just confirm Einstein's predictions, they've completely reshaped how we see the universe. Think of the cosmos as a vast, intricate tapestry, woven together by the threads of these ripples in spacetime. Each time two black holes collide, or neutron stars spiral into each other, they send out waves that ripple across the fabric of the universe, connecting events that happened billions of years ago with the present moment. It's as if the cosmos itself is telling us its story, one wave at a time. This metaphor of the cosmic tapestry is more than just poetic, it's a profound shift in perspective. Before gravitational waves, we saw the universe as a collection of isolated events, separated by vast distances and time. But now, we understand that these events are deeply interconnected, bound together by the invisible threads of spacetime itself. Gravitational waves carry information about the universe's most violent and energetic processes, offering us a front-row seat to phenomena that were once hidden from view. This new way of seeing the universe challenges some of our most fundamental notions about space and time. Instead of thinking of them as fixed and unchanging, we now see them as dynamic, almost alive, stretching, compressing, and rippling in response to the movements of massive objects. It's a universe that's constantly in motion, a living, breathing entity where every action sends ripples across the cosmic fabric, and this is just the beginning. With each new detection, we're not only learning more about the universe, we're also opening up entirely new avenues of exploration. The future of gravitational wave astronomy promises even more discoveries, from uncovering the secrets of dark matter to mapping the earliest moments of the Big Bang. These waves are more than just a tool for observation, they're a window into the very heart of the cosmos, revealing a universe that's far more dynamic and interconnected than we ever imagined. As we peer into the future of gravitational wave astronomy, the horizon is brimming with possibilities. The next generation of detectors, both on Earth and in space, promises to revolutionize our understanding of the cosmos. Ground-based observatories like the Einstein Telescope and Cosmic Explorer are being designed with unprecedented sensitivity, capable of picking up signals from events billions of light years away. These advanced instruments will allow us to detect gravitational waves from sources too faint or distant for current technology to capture, opening a new window into the universe's most elusive phenomena. But the quest doesn't stop at Earth's surface. Space-based detectors, such as the Laser Interferometer Space Antenna, or LISA, will take the search to the stars. Floating far from Earth's noisy environment, LISA will detect low-frequency gravitational waves that ground-based observatories simply can't access. This will give us a front-row seat to events like the mergers of supermassive black holes, which occur on timescales too slow for Earth-based instruments to observe. With these advancements, we're not just improving our ability to detect known sources, we're unlocking the potential to discover entirely new ones. Imagine catching the faint whispers of cosmic strings, hypothetical one-dimensional objects left over from the early universe, or encountering exotic compact objects like boson stars, which challenge our understanding of matter itself. These discoveries could reshape our knowledge of physics, revealing secrets about the fundamental nature of the cosmos. As we stand on the brink of these breakthroughs, it's impossible not to wonder how they'll ripple through science and society. The insights gained from these next-generation detectors could answer some of humanity's most profound questions about the origins of the universe, the nature of space-time, and the forces that govern it all. And as we continue to listen to the hidden symphony of gravitational waves, we're not just exploring the cosmos, we're redefining our place within it. Gravitational waves are not just ripples in space-time, they're cosmic messengers, carrying secrets about the very fabric of the universe. These waves allow us to test the laws of physics in ways that were once unimaginable. Think of them as a natural laboratory, one where extreme conditions like colliding black holes or neutron stars push the boundaries of what we know about gravity, space-time, and the fundamental forces that govern our universe. One of the most fascinating aspects of gravitational waves is their ability to probe the nature of gravity itself. Einstein's theory of general relativity has been the cornerstone of our understanding for over a century, predicting how massive objects warp spacetime and create these ripples. But what if there's more to the story? Gravitational waves give us a tool to search for tiny deviations from Einstein's predictions. If we find them, it could mean we're on the brink of uncovering new physics, and perhaps even a glimpse into quantum gravity or hidden dimensions. Take black holes, for example. These mysterious objects are perfect testing grounds. When two black holes collide, they create gravitational waves that carry information about their masses, spins, and even the shape of spacetime around them. By analyzing these signals, scientists can check if black holes behave exactly as general relativity predicts, or if there's something unexpected lurking in the data. It's like listening to the universe's heartbeat, searching for irregularities that might reveal deeper truths, but the implications go beyond black holes. Gravitational waves also let us explore the very nature of spacetime. Is it truly continuous, as Einstein suggested, or could it have a granular, quantum structure at the smallest scales? These waves might hold the key to answering questions that have puzzled physicists for decades. Every detection brings us closer to understanding the universe's most fundamental laws and possibly rewriting them. Behind these groundbreaking discoveries lies an incredible human story. Thousands of scientists, engineers, and dreamers have dedicated their lives to detecting these faint whispers from the cosmos. It's a reminder that science is not just about equations and theories. It's about curiosity, collaboration, and the relentless pursuit of knowledge. And as we continue to unravel the mysteries of gravitational waves, we're not just exploring the universe, we're exploring what it means to be human in the face of the infinite. For decades, scientists around the world dreamed of hearing the whispers of the cosmos' gravitational waves, but turning that dream into reality wasn't just about equations or cutting-edge technology, it was about people. Behind every breakthrough were individuals who poured their lives into this monumental quest. Take, for instance, Barry Barish and Kip Thorne, two of the key figures behind the Laser Interferometer Gravitational Wave Observatory, or LIGO. Thorne, a theoretical physicist, spent years working on the math that predicted these ripples in spacetime, while Barish, an experimental physicist, led the team that built the instrument capable of detecting them. Together, they embodied the perfect blend of theory and practice, imagination and execution. But the story of gravitational waves isn't just about a few names, it's about thousands of collaborators across the globe. Scientists, engineers, and technicians from dozens of countries worked tirelessly, often facing setbacks that could have ended the project. Early prototypes failed. Funding was uncertain, and for years the detectors remained silent, picking up nothing but noise, yet the team persisted, refining their instruments, tweaking their algorithms, and waiting for the universe to give them a sign. Then, on September 14, 2015, it happened. A signal, faint but unmistakable, reached Earth. It was the sound of two black holes colliding over 1 billion light-years away. For those who had spent their careers chasing this moment, the discovery was overwhelming. Some described it as hearing the universe speak for the first time. Others said it felt like witnessing the birth of a new era in astronomy. The emotional weight of that moment is hard to overstate. It wasn't just a scientific triumph, it was a deeply human one, a testament to what we can achieve when we work together toward a shared vision. This discovery also holds profound cultural significance. For centuries, we've looked to the stars and wondered about our place in the cosmos. Gravitational waves offer a new way to explore that question, allowing us to listen to the universe rather than just observe it. They remind us that science isn't just about facts and figures, it's about curiosity, creativity, and the enduring human drive to understand the unknown. And as we continue to uncover the secrets of the cosmos, these ripples in spacetime will forever echo the stories of those who dared to listen. Gravitational waves have not only revolutionized our understanding of the cosmos, but have also woven themselves into the fabric of popular culture. From the silver screen to the pages of novels, these ripples in spacetime have captured the public's imagination in ways that few scientific discoveries have. Think about movies like Interstellar, where the concept of spacetime bending and gravitational waves plays a central role in the story. Or consider how authors like Kip Thorne have brought these phenomena to life in books, making the abstract feel tangible. Even in art, gravitational waves have inspired stunning visualizations, turning the invisible into something that stirs both curiosity and wonder. But it's not just about entertainment. The portrayal of gravitational waves in popular media has a profound impact on how we perceive science. For many, these depictions spark a sense of awe and curiosity, planting the seeds for future scientists and engineers. Imagine a young person watching a documentary or reading a sci-fi novel, and suddenly realizing that the universe is far more dynamic and mysterious than they ever imagined. That moment of inspiration could set them on a path to uncovering the next great cosmic secret. It's a reminder that science communication isn't just about explaining facts, it's about igniting passion and making complex ideas feel approachable. Making science accessible is crucial, especially when it comes to groundbreaking discoveries like gravitational waves. When people can connect with these concepts through stories, art, or film, it bridges the gap between the scientific community and the public. This connection fosters a deeper appreciation for the work being done and the challenges being tackled. And as we marvel at these discoveries, it's worth pausing to consider the ethical dimensions of this research. What responsibilities do we have as we explore the universe's deepest secrets? How do we ensure that the knowledge we gain is used to benefit humanity as a whole? These are questions that bring us to the next chapter of our cosmic journey. Gravitational wave astronomy opens up a universe of possibilities, but it also invites us to pause and consider the ethical dimensions of this groundbreaking research. As we push the boundaries of our understanding, questions arise about how we allocate resources to such ambitious projects. With funding often limited, is it justifiable to invest billions in detecting ripples in spacetime when pressing issues like climate change and global health demand attention? This isn't a simple question, but it's one worth exploring. The pursuit of knowledge has always been a balancing act, where the drive to explore the cosmos must coexist with the need to address challenges here on Earth. Another layer of ethical consideration lies in the potential for dual-use technologies, tools developed for gravitational wave detection that could be repurposed for other applications, including military or surveillance purposes. While the primary goal of this research is to expand our understanding of the universe, the unintended consequences of technological advancements can't be ignored. This raises a vital question. How do we ensure that the fruits of scientific discovery are used responsibly and for the benefit of all? International collaboration plays a crucial role here. Gravitational wave astronomy is a global endeavor, with observatories like LIGO in the United States, Virgo in Europe, and CAGRA in Japan working together to detect these elusive signals. This spirit of cooperation underscores the importance of equitable access to scientific discoveries. Knowledge about the cosmos should belong to everyone, not just the nations or institutions with the resources to fund such projects. By fostering inclusivity and sharing data openly, we can ensure that the benefits of this research reach beyond borders and inspire future generations everywhere. Beyond the ethical and collaborative aspects, gravitational wave astronomy has a profound educational impact. The excitement surrounding these discoveries sparks curiosity in students and the public alike, offering a gateway to understanding complex concepts like spacetime, black holes, and the very nature of the universe. By making this field accessible through outreach and education, we can inspire a new wave of scientists, engineers, and thinkers who will carry the torch of exploration into the future. And as we continue to unravel the mysteries of gravitational waves, we're not just learning about the cosmos, we're also teaching the world how science can bring us closer together. Gravitational waves aren't just reshaping our understanding of the cosmos, they're also transforming how we teach and learn about science. Across the globe, educators are weaving the story of these cosmic ripples into classrooms, from high schools to universities, turning abstract concepts into tangible, awe-inspiring lessons. Imagine sitting in a physics class where, instead of just reading about Einstein's predictions, you get to explore real data from LIGO or Virgo, witnessing firsthand how these detectors capture the whispers of colliding black holes millions of light years away. This isn't just science fiction anymore, it's science in action, and it's becoming a cornerstone of modern education. But it's not just about textbooks and lectures. Citizen science projects are opening the doors for anyone, anywhere, to participate in this groundbreaking research. Platforms like Gravity Spy invite everyday enthusiasts to help classify data, sifting through signals to identify potential gravitational wave events. It's a powerful way to democratize science, giving people a front-row seat to discoveries that were once the exclusive domain of astrophysicists. These projects don't just engage the public, they inspire a deeper connection to the universe, showing that science is a collective endeavor, not just something that happens in labs or observatories. What makes this shift so exciting is its potential to nurture curiosity and critical thinking in the next generation. By introducing students to the mysteries of gravitational waves, educators aren't just teaching physics, they're encouraging young minds to ask big questions, to challenge assumptions, and to see themselves as part of a larger quest for knowledge. And in a world where scientific literacy is more important than ever, fostering that sense of wonder could be one of the most transformative gifts we give to future scientists, engineers, and thinkers. As we look ahead, the integration of gravitational wave astronomy into education isn't just about creating better scientists, it's about shaping a more informed and engaged humanity. It's a reminder that the cosmos isn't just something we observe from afar, It's something we're all connected to, part of a story that's still being written. And as we continue to explore that story, we're not just uncovering the secrets of the universe, we're also discovering what it means to be curious, to collaborate, and to push the boundaries of what's possible. Gravitational waves are not just ripples in spacetime, they are a bridge between humanity and the vast, mysterious universe we inhabit. When we detect these waves, we're essentially listening to the whispers of cosmic events that happened billions of years ago, colliding black holes, merging neutron stars, and the birth of galaxies. It's a humbling reminder that we are part of something far greater than ourselves, a tiny speck in a cosmic tapestry woven over eons. This connection isn't just scientific, it's deeply emotional. It sparks a sense of wonder, a feeling that we are witnessing the universe's grandest stories unfold in real time, but this connection goes beyond awe. Understanding gravitational waves invites us to reflect on our place in the cosmos. We are not just passive observers, we are active participants in the universe's ongoing narrative. This perspective can shift how we see ourselves and our responsibilities. If the universe is vast and interconnected, then so are we. The challenges we face, climate change, inequality, and global conflict, are not isolated problems. They are threads in a larger fabric, much like the gravitational waves that ripple across the cosmos. Just as we've learned to detect and interpret these waves, we can apply the same curiosity, collaboration, and determination to solve the pressing issues of our time. This knowledge also unites us. Gravitational wave astronomy is a global effort, requiring telescopes, detectors, and scientists from every corner of the world to work together. It's a reminder that when we pool our resources, share our knowledge, and focus on a common goal, we can achieve extraordinary things. The study of gravitational waves isn't just about understanding the universe, it's about understanding ourselves and our potential to create a better future. So, what does all this mean for us? It means that the universe is not just out there, it's here, within us, shaping our perspective and inspiring us to think bigger. Gravitational waves remind us that we are part of a grand, interconnected story, and that story is still being written. As we continue to explore the cosmos, we're not just uncovering its secrets, we're discovering our own capacity for wonder, collaboration, and growth. As we bring this exploration to a close, let's take a moment to reflect on the incredible journey we've taken together. Gravitational waves, those ripples in spacetime first predicted by Einstein over a century ago, are far more than just a scientific curiosity. They are a profound tool for unlocking the secrets of the cosmos, allowing us to witness events like colliding black holes and neutron stars in ways that were once unimaginable. These waves have opened a new window into the universe, revealing its hidden symphonies and reshaping our understanding of reality itself. But the impact of gravitational waves extends beyond the realm of science. They challenge us to think deeply about our place in the universe, reminding us of the interconnectedness of all things. From the violent collisions of distant stars to the subtle vibrations they send across the cosmos, these waves tell a story of a universe that is alive, dynamic, and ever-changing. They inspire awe and wonder, bridging the gap between the scientific and the philosophical, and inviting us to ponder the mysteries that lie beyond our current understanding. This journey has shown us that the universe is not just a collection of objects, but a tapestry woven together by forces we are only beginning to comprehend. Gravitational waves are the threads that connect us to the farthest reaches of space and time, offering glimpses into events billions of years in the past. They remind us that science is not just about answering questions, but about asking new ones, about pushing the boundaries of what we know and daring to explore the unknown. As we conclude, let's carry this sense of curiosity and wonder with us. The study of gravitational waves is still in its infancy, and there is so much more to discover. Every detection brings new insights, new mysteries, and new opportunities to deepen our connection to the cosmos. Whether you're a scientist, a space enthusiast, or simply someone who marvels at the beauty of the universe, these waves remind us that we are all part of something much larger than ourselves, a cosmic story that continues to unfold with every ripple in spacetime. As we stand at the edge of what we know and gaze into the vast unknown, the story of gravitational waves reminds us just how far human curiosity and ingenuity can take us. Over a century ago, Albert Einstein imagined ripples in spacetime, a concept so daring it seemed almost impossible to prove. Yet today, thanks to the tireless efforts of scientists, engineers, and dreamers, we've not only detected these elusive waves, but also used them to listen to the universe in ways Einstein himself might never have imagined. Each collision of black holes, every merger of neutron stars, sends out a cosmic symphony, and we've learned to tune in. It's a testament to what happens when we dare to ask big questions and work together to find the answers. Gravitational wave astronomy is more than just a scientific breakthrough. It's a reminder that the universe is full of stories waiting to be heard. It shows us that the cosmos isn't silent. It's alive with vibrations, whispering secrets about the nature of space, time, and existence itself. But none of this would have been possible without the power of collaboration. From the LIGO detectors to international partnerships, this journey has been a global effort, proving that when we unite in pursuit of knowledge, there's no limit to what we can achieve. So what's next? The discoveries we've made so far are just the beginning. With every new detection, we're peeling back another layer of the cosmic tapestry, uncovering mysteries that could redefine our understanding of reality. And that's the beauty of science. It's an endless adventure, one that invites all of us to be explorers in our own way. Whether you're a scientist, a student, or simply someone who looks up at the night sky in wonder, the story of gravitational waves is a reminder that the universe is vast, mysterious, and full of possibilities. To close, let's take a moment to reflect on the words of the great Carl Sagan. Somewhere, something incredible is waiting to be known. Gravitational waves have shown us that the incredible is not just out there, it's within our reach. So keep asking questions, stay curious, and remember that every discovery, no matter how small, brings us closer to understanding the grand symphony of the cosmos. If this journey has sparked your imagination, let us know in the comments below. What do you think we'll discover next? And don't forget to subscribe for more cosmic adventures. The universe is waiting, and the story is far from over.